Are continuing week 3 conservation laws. This is part 4 of this week lecture. So we just introduced briefly the notion of potential energy, and we said that it was related to the kinetic energy. Recall that when you have a ball drop from a height h, it accelerates and gains kinetic energy. And so what happens here is, the way we think of this is that at that height h, the potential energy is mgh. As the ball falls, its potential energy will decrease and its kinetic energy will increase. So effectively, potential energy will be transformed or converted, if you will, into kinetic energy. So when a ball is falling, it loses potential energy and gains kinetic energy. If instead you throw the ball up from the ground, you will impart large kinetic energy to the ball, and it will go up, 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 slow down, and eventually reach a maximum height. And so as it goes up, kinetic energy will progressively be converted into potential energy. At some point, the kinetic energy will go to zero, and the potential energy will be maximum. At that point, unless somebody is catching the ball's motion will be reversed. The ball will come back down to the ground, so it will lose potential energy and gain kinetic energy. And in the absence of friction, it will come back to the ground at the same kinetic energy it had when leaving the ground. A similar phenomenon can happen or will happen when you compress a spring. So if you have a slinky where you compress it or stretch it, stretching or compressing the slinky will cost energy. So if you have kinetic energy coming in, you have an object with kinetic energy coming in, and it hits the spring, it will compress the spring. Kinetic energy will be transformed into spring potential energy. This spring will be then increasing in potential energy until the kinetic energy reaches a value of zero. If nothing is stopping the object at that point, the spring will stretch back, and so potential energy of the string will then be converted into accelerating the object. So potential energy of the string will be converted into kinetic energy of the object. So you can see that either in a fall under gravity or in an acceleration due to a spring, you have conversion of kinetic energy into potential energy and back potential energy into kinetic energy. Okay, so now we saw that if you have a spring, you can say, well, I compress the spring, so there is energy converted into the spring. How is this energy converted? Well, it means that something in the spring is building tension in the spring. So there's a tension being built into the spring because of its mechanical nature, because of its makeup. And when you release the spring, this energy will be released, so the spring will unravel, it will expand, and will accelerate whatever objects you have on it. So the potential energy is stored into the spring in the form of internal mechanical energy, if you will. So it's basically a stress inside the spring, which involves the structural components of the spring, the mechanical, the atoms composing the string. You can obviously ask yourself then, okay, what's the equivalent for gravitational energy? Right? So when you launch a ball and it reaches a height h, you've converted kinetic energy into potential energy. And you could say, what is storing this? How is this potential energy stored? The answer is the gravitational field. Okay, so with these two concepts of kinetic energy and potential energy, we actually can describe the motion of a lot of things, or what's happening on a lot of things around us, be it a baseball, a golf ball, what's happening to rocket, planes, and automobiles, and so on and so forth. And so let's look at some examples. First, let me remind you of the quantities that we're dealing with. Kinetic energy is 1/2 the mass times the square of the velocity of an object. The gravitational potential energy is mgh. When you have a fall of an object under gravity without friction, the change in potential energy will be equal to the change in kinetic energy. The potential energy of gravity associated with gravity is mgh. Consequently, it will be equal to 1/2 mv squared. So now I have mgh, the mass of the objects, gh, time equals 1/2 the mass of the object v squared. It's the same mass, so I can cancel that out. I'm left with gh equals v squared over 2, which I can now rearrange as h equals v squared over 2g. So that means that if I now have a ball and I throw it up vertically at some velocity, and let's say 14 meters per second, then this ball will travel to a certain height. The height numerically will be 14 squared divided by 2 divided by g, 9.8 meters per square second, and that amounts to 10 meters. If you double the speed, then because of the v squared, the height will be increased by a factor of 4. If you decrease the speed by a factor of 2, the height will be decreased by a factor of 4. So put that into application right now. You drop a rock from a height of 10 meters in free fall, assume or neglect air resistance. You can then ask, how fast is the rock going when it hits the ground? Right? How fast is it going? So think about it. You convert potential energy into kinetic energy. We saw that there's a simple formula relating the two. The formula, as it happens, does not depend on the mass of the object. And so you don't need the mass here to solve this problem. I'll let you think about it for a second. So if you go back to the formula here, you can reapply it and figure out that you can, instead of solving for h, now you have a relationship which is h equal v squared over 2g. Now you can solve for v, and you will find that the velocity of the object as it reaches the ground is 14 meters per second. Let's consider another problem, that of Cedar Point. Some of you may love roller coasters. I used to, but now they mostly make me sick to my stomach. Be that as it may, consider that you are in a cart at the top of a roller coaster, let's say at a height of 10 meters, as illustrated here, and you are then rolling down the roller coaster, and as you reach the bottom, you will have achieved a certain velocity v. Evidently, in a real roller coaster, there is friction involved within the cart. Between the cart and the wheels of the car have some friction. So there will be some energy loss there. So not all the potential energy will be converted into kinetic energy in a real situation. But here, let's assume that this is verified, that all the energy is translated or transformed into kinetic energy. So what will be the velocity of the cart at the bottom of the slope? So we saw that for a height of 10 meters, the velocity would be 14 meter per second. So what will be the velocity of the cart in relationship to this particular velocity? Again, we neglect friction. Think about it for a moment. It will be the same. It doesn't, if friction can be neglected, if all the potential energy is translated or converted into kinetic energy, then the shape of the trajectory, the shape of how you go to height h of 10 meter to 0, that shape or that trajectory does not matter. And so it's only the height that matters. So you go from a height of 10 meter to a height of 0, and so that leads to a conversion of potential energy into kinetic energy. And so the mass doesn't matter, so you have the same velocity, same speed rather. Let's talk a little bit about this a little more, in a little more depth. So when an object is falling or going up, gravity is applying work on the object, is applying a force onto the object, and this force is either accelerating down or slowing the object as it moves up. The amount of work is the product of the force by the distance, but it is also equal, as it happens, to the potential energy of the object. So the force is mg, the height is h, and so that's the force times distance. So one has to apply a force, and here the force is of constant magnitude over a displacement h. So one has done a work, what do we call a work, and this work then has created this potential energy. This work has transformed the kinetic energy and stored it into the gravitational field of the Earth. And so the work is the force times the displacement, F equal D. F equal D when the force is in the same direction as the displacement. And the units of work are newtons, force, times meter, displacement. So that's equivalent to kilogram square meter per square second, which happens to be equivalent to 1 joule. That is, work has the same unit as energy. So work can be done to bring an object up or down, and it is also used to change the kinetic energy of an object. So work can change the potential energy or the kinetic energy, or both. So let's do a specific example of a calculation. We have a force of 1,000 Newton applied onto a vehicle of 1,000 kilogram, and let's pretend that it is applied for 10 seconds. So the acceleration is we get from F equal ma, so A equals F over m, and the force is 1,000, the mass is 1,000, so 1,000 over 1,000 is numerical value of 1, so the acceleration is 1 meter per square second. Let me fix this as I see it. Apologies for this. And so that's the acceleration. The distance traveled during these 10 seconds will be d equal 1/2 at squared. Remember this formula we've seen before. And so that is 1/2 times 1 times t squared, which is t is 10 seconds, so that's t to the power 2, 100. 100 divided by 2 is 50 meter. So the force is applied through a distance of 50 meter. The velocity change will be from 0 to some value. The value will be AAT, 1 times 10. That's 10 meter per second, the final velocity. The kinetic energy will be starting at 0, but then reach a value of 1/2 mv squared. That's 1/2 times 1,000 times the square of 10. And so that's 50,000 joules. Independently, I can also compute the work being done. The force is 1,000 Newton and the distance is 50 meter. And that corresponds to 50,000 joules. So you see that the work being done on an object to accelerate it during 10 seconds is equal to the change in kinetic energy of that object. Another example, a ball with mass m of 0.1 kilogram is thrown up. What work has to be done to make the ball move upward with v equal 10 meter per second at the point of release? So you are trying to accelerate the ball. You have to do work on the ball to put it in action, to put it in motion. So it goes from a velocity of 0, and then you want to accelerate it to 10 meter per second when you release it. And so you know then that it will go from a kinetic energy of 0 to a kinetic energy corresponding to 1/2 mv squared. So then the work done will be used to accelerate and change the kinetic energy from 0 to the final kinetic energy of the ball. What is this value? I'll give you a moment to think about it. It is 5 joule. Next question is, when is the work done on the ball by the person throwing the ball, right? How does that work? When one is the baseball player doing the work done on the ball to change the velocity of the ball from 0, essentially, to whatever speed it has when the ball is really is going, right? So I'll let you think about that for a moment as well. So the work is being done by the baseball player, or technically the hand of the baseball player onto the ball. And so the baseball player propels his hand with all his arm, right? Propels his hand, and as such propels the ball in some direction. And so the baseball player accelerates the ball from 0 velocity to some high velocity. And this happens while the baseball player is actually holding the ball. And we'll stop now until part 5.